Hello, and thank you for joining us. Today's webinar topic is Helium Conservation in Purge and Trap Analysis. Our presenter is Amy Nutter, VOC Technical Product Specialist for Teledyne Tekmar. If you have any questions, please feel free to submit them throughout the presentation or email Amy directly, and she will follow up with you once the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Amy Nutter.
Hi, thank you for the introduction. I'm Amy Nutter, Technical Product Specialist for the Purge and Trap product line here at Teledyne Tekmar. And today I will be going over ways to conserve helium during your Purge and Trap analysis. As helium supplies become scarcer and more expensive, you may have been seeking alternative carrier gases or purge gases or ways to conserve helium without sacrificing system performance. So I will cover a few ways that you can achieve this. Thanks for joining me today. I'll go over a quick intro to Teledyne Tekmar and our products. Then I'll get into what Purge and Trap is and how it works, getting into the alternatives to helium purge gas. And then I will show you some purge parameter comparisons that you can try in order to conserve as much helium as possible if you decide to continue using helium as your purge gas. So be sure to submit any questions that you have. I will be able to answer those by email. Teledyne Tekmar has been around since the 60s, creating the first commercial purge and trap concentrator in 1975. We're the market leader for purge and traps in the US, and we offer several different options. The Lumen Purge and Trap concentrator, shown on the right, is our standalone waters-only concentrator, and that can be paired with the Aquatech LVA auto sampler. We also have the combined auto sampler and Purge and Trap concentrator, the Atomic XYZ, shown on the left, which is capable of analyzing soil, solids, and water samples. We also manufacture other elemental analyzers as well. Purge and Trap is a technique used to improve the sensitivity of volatile samples analyzed by a GC and their detectors, such as a mass spec. And it goes beyond the capabilities of other traditional preparation methods like static headspace and liquid injections. So we are talking parts per billion levels, and recently we've been optimizing parameters to reach down to those parts per trillion analysis levels. Some common VOCs are disinfection byproducts from chlorine treatment, gasoline, which is made up of many volatile compounds, ethanol found in beer, acetone in nail polish remover, mineral spirits in paint thinner, and hexane in glues. Now let's get into how this works. Purge and Trap works on a purge equilibrium theory or a disequilibrium theory, meaning that volatile compounds of interest, compounds that prefer to be in that gaseous phase, migrate from the liquid or the solid phase into the gaseous phase and are continuously swept away from that headspace in the sparger onto the trap where they're concentrated and then released to the GC. In the case of static headspace on the left, samples come to an equilibrium. The compounds of interest go from the liquid to the gaseous phase, and when no more net transfer is occurring, an aliquot of that headspace is taken and analyzed. So if we don't see enough sensitivity from this analysis during this static headspace, then that's where Purge and Trap can improve. On the right, we can visually see that purge equilibrium theory happening. The VOCs that are moving into the gaseous phase are constantly being removed from the purge gas. Continuously replacing that headspace is what causes the disequilibrium, in that there's always a higher concentration of VOCs in the liquid phase than in the gaseous phase, continuing that net movement of VOCs from liquid to gas, extracting the VOCs from the sample more efficiently and improving sensitivity because there's just more of those compounds to analyze. A basic purge and trap consists of 5 main parts: the sparger, flow control, 6-port valve, analytical trap, and the heated transfer line. So the sparger is that glassware on the front of the instrument that receives the liquid sample to be purged. Purging the sample extracts VOCs by dispersing inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or pressure regulator that monitors and precisely controls the gas flow rate throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. So trapping these VOCs helps create a smaller band of analytes traveling to the GC column, producing greater signal-to-noise ratios and lower area-to-height ratios, generating sharper peaks and better sensitivity and resolution. So once the VOCs are captured, the trap is heated and carrier gas is backflushed through the trap, causing the VOCs to desorb. The 6-port valve then directs the VOCs through the heated transfer line to the GC for separation and detection by the mass spec. So alternatives to helium as a carrier gas. So these alternatives, they come with trade-offs. They can often cause shifts in retention time. They can cause separation issues. They might require significant method parameter changes and validation times. So hydrogen as a carrier gas, it can be corrosive, explosive. It can cause those VFB tune criteria passing issues. So definitely some safety concerns with using hydrogen. You don't want those levels to build up over, concentrations. So we need proper venting of the GC, and we need to ensure that the mass spec vacuum stays good and that the whole system stays leak tight. Most newer GCs, these days are ensuring that these safety concerns are being taken care of. Out there, we see a lot of customers, trying to make the switch to the hydrogen carrier gas because it is that much cheaper. Nitrogen as a carrier gas can have poorer separation, and again, dealing with those VFB tune criteria passing issues as well. And that's just because the VFB tune criteria, it was written around helium as a carrier gas, and that's why these alternative carrier gases have trouble sometimes. So getting into the characteristics of a great purge gas for VOCs would be that it must be inert, meaning it can't react with the VOCs or anything else in the sample. It cannot be combustible or unstable, such as hydrogen. For our instruments, during desorb, the trap is closed off and it's heated, and that builds up pressure, and it can cause problems for such a combustible compound such as hydrogen or oxygen. So purge gas must be free of those VOCs. Usually the standard is 5/9 pure gas. You don't want to contribute to the total VOCs in the sample collected and create false positives or contaminate your blanks. Helium is the traditional purge gas of choice because of its superior inertness, stability, and compatibility with the GCMS, but it can be somewhat expensive and occasionally difficult to get. So nitrogen can be a good alternative to helium because it has similar inertness, it's low cost for cylinders, and it has the ability for generators to produce it. Because nitrogen is a larger molecule, it goes through the GC column first, which can occasionally have a minor effect on purge efficiency and mass spec vacuum during desorb and pump down. But it often provides more than adequate purge efficiency for compounds of interest under standard EPA parameters. So switching the purge gas to nitrogen is very easy to do with the Tekmar Purge and Trap in the TechLink software. It's just a drop down in the configuration in the tools menu. It can leak check, and it calculates the flow rate based on which purge gas you choose. So thanks to our mass flow controller, few to no significant changes in the purge and trap method has to occur to be able to run a different purge gas. So the mass flow controller, which is available on the Atomics XYZ and the Lumen, it monitors and precisely controls the gas flow rate throughout the entire purge and trap process. So once it's set, the parameters remain precisely controlled throughout all nodes of operation, and it achieves highly reproducible analysis. So since changing the carrier gas can lead to a lot of time-consuming activities like method and data validation, what are our other options? Changing the purge gas. So typically, purge and trap concentrators use up to 1,200 mils of gas per active sample and up to 1,200 mils per hour in standby mode. So alternative purge gases can lead to significant cost savings. Like I mentioned before, nitrogen is inexpensive, generators can produce it, cylinders don't cost very much, and often it provides adequate purge efficiency under those standard EPA parameters. Hydrogen is not an option for purging. During desorb preheat, it seals off the trap and heats it up to 250 degrees C in some cases. So that would definitely cause an explosive environment by pressuring that hydrogen under heat and cause a dangerous situation. So here I just wanted to compare helium versus nitrogen as a purge gas. These are 524 series compounds, both pretty default method settings, 11-minute purge at 40 mils a minute. And as you can see, it's pretty comparable throughout the entire tick. And then I went ahead and zoomed in on those early eluting compounds. Again, the black peaks being helium, red being the nitrogen peaks. Pretty comparable across the board there. And then I went ahead and zoomed in on the middle eluting compounds. And then the back end compounds, again with black being the helium purge gas and then red being the nitrogen purge gas. Across the board, really good purge efficiency with both. We can also control the volume of gas that we use. So the longer that we continue to sweep that headspace away, the more volatile compounds we can extract from the sample. When considering purge volume, first we want to look at the flow rate. So basically how many minutes or the amount of time we are purging and how fast, which would be the flow. A fast flow means that more purge gas is used in the same amount of time. And a really aggressive flow can cause pressure issues, or they could push compounds of interest deep into the sorbent bed of the trap. We also want to look at purge time. So the longer that we're purging, the more purge gas we are using. And if we purge for too long, it can waste a lot of gas and again, push those compounds of interest deep into the sorbent bed of the trap. So it's all about finding that balance and what works best for your system. So therefore, as our purge volume and time are increasing, they get to that point where the response starts to plateau. And then eventually you start to lose response because those compounds are getting stuck in the sorbent bed of the trap, which can lead to a waste of time and gas, which means ultimately a waste of your resources. So method 524.3 is used to analyze drinking water samples. It has less compounds on its list than 524.2. And it also allows for this method flexibility where we have the chance to conserve helium. The flexibility is in order to, reduce that sample processing time but it does come with pretty strict QC requirements. So this method allows you to optimize purge and trap parameters to maximize purge efficiency and minimize the transmission of water to the GC. There are 5 key parameters listed here on the table, and then it shows you kind of the recommended and allowable ranges for our flow rates and times. So what I wanted to compare and show you today was the minimum for the recommended and allowable flow rates and times in this table. I also compared the minimum with the maximum allowable, recommended and allowable, just to give you, another comparison. So if you're still using helium to purge, hopefully this is a decent comparison to see if you might want to try and change your total purge volume, change a few parameters in order to help you conserve helium. So here I varied the purge volume. Both of these are at a 4-minute purge time. The black peaks are a 4-minute purge at 60 mils a minute, and the red peaks are a 4-minute purge at 90 mils a minute. So this would be comparing the minimum allowable 240 mils total volume and the minimum recommended 360 mils total purge volume from that table that I just showed you. So these two seem to be pretty comparable, with some compounds displaying higher purge efficiency with that 240 mils a minute total purge volume, especially at the front end and the late eluting compounds. All right, and here I just varied the purge volume again, 6-minute purge time. The black is a 6-minute purge at 40 mils a minute, and the red peaks are the 6-minute purge at 60 mils a minute. Again, comparing those minimum allowable and minimum recommended from the table, just a little bit more purge time. So here we can see really great purge efficiency from that 240 mils per minute total purge volume, just across the board, across the whole tick. All right, and here I varied the purge time with the minimum allowable total purge volume at the 240 mils per minute. So I saw, really good purge efficiency from that 240 mils per minute total purge volume. So I kept that. I just wanted to vary the purge time and flow to get there. So the black peaks are the 4-minute purge at the 60 mils per minute, and the red peaks are a 6-minute purge at 40 mils per minute. This displays a really great purge efficiency from that 6-minute purge at 40 mils a minute. Again, like the graph I kind of showed you, you just have to kind of find your sweet spot when you're using the same total volume. So these compounds maybe just needed a little bit more purge time to get there. All right, and here I varied the purge time with the minimum recommended total purge volume. It's kind of like before, I kept that 360 mils per minute total purge volume, but I varied the purge time and flow. So the black peaks here are a 4-minute purge at 90 mils per minute, and the red peaks are a 6-minute purge at 60 mils a minute. Here we see pretty even purge efficiency across the tick. So from that table, this is the minimum allowable versus the maximum recommended total purge volume. So the black peaks are that 6-minute purge at 40 mils a minute, being a 240 mil total purge volume, and the red peaks being a 6.5-minute purge at 80 mils per minute. I also did a 2-minute dry purge in there at 100 mils per minute with a total purge volume of 720 mils per minute. So here we can see Really great purge efficiency from both. And if you're looking at, total purge volumes, with that 720 mils per minute being slightly more efficient, across the tick, but 240 total still performs well, and it'll save you 480 mils per minute per sample. So it's definitely worth exploring. All right, and here I have the minimum allowable versus the maximum allowable. Again, the black being that 6-minute purge at 40 mils per minute for a total purge volume of 240. And the red, it was a 3.4-minute purge at 200 mils per minute with a 2-minute dry purge at 100 mils per minute, totaling 880 mils per minute total purge volume. So I think the 880 was just a little bit too much flow here, and it's just not creating a very efficient purge. So across the tick, we've got that 240 mils per minute total purge volume just being a lot more efficient with these compounds. And lastly, I wanted to compare the minimum allowable versus just the default method. So with our default being in red, that would be an 11-minute purge at 40 mils a minute. I think there's 1-minute dry purge in there too, at 100 mils per minute. So overall, pretty comparable across the tick. There are a few compounds where that default method is, has better purge efficiency, but overall, being able to save 300 mils per minute, because that includes the 100 mils per minute of the dry purge, that can really help you save and conserve helium in the long run. So if you're interested, the 6-minute purge at 40 mils per minute with only 240 total purge volume, it could work out for your system. So it's something definitely worth exploring if you can pass that strict QC criteria. I just did a zoom in to show you how comparable they were across the board. So here, you have a few compounds that are more efficient with the default method. And then across the middle, compounds. And then here is the back end compound. All right, and in conclusion, nitrogen as a purge gas, it is adequate for most methodologies, including popular EPA methods. It requires very few purge method adjustments. It's easily configured in our Tekmar purge and trap systems. You just click a few buttons, and the mass flow controller takes care of it. Nitrogen is an excellent purge gas for those who want to reduce operating costs, want to buffer against uncertain helium supply, and don't want to compromise chromatographic quality or invest development time into alternative carrier gas methods. So with that helium purge gas, a way that you can save or conserve some of that helium, I really found that 6-minute purge at 40 mils a minute for that total purge volume of 240, which was the minimum allowable in 524-3 method. I thought it looked great. It could save a lot of helium in the long run. But like I mentioned before, 524.3 does have some pretty strict QC requirements. So, if you could just have a little bit faster of a purge with less volume, and if it works for your systems, that's great. It might save you some helium in the long run. Thank you so much for taking time out of your day to join me. Please check out our website for all of our latest application notes. You can view past webinars, you can visit our online store, and you can follow us on social media too. Also, please submit any of those questions that you have, and I'll be able to get back to you by email. Thank you. Have a great day.